okay, depending on the temperature, obviously, and you'll get some water vapor being formed on the top above the liquid. Once it reaches equilibrium, then there is no evaporation taking place. Or we say that the rates at which evaporation and condensation occurs is exactly the same, so that there's no physical change in mass transfer. Okay, so the liquid level remains exactly the same. For us to have mass transfer taking place, there must be non-equilibrium. Okay, so we got to say that the concentration in the liquid phase is different to the concentration in the gaseous phase. And when that occurs, when that non-equilibrium occurs, then we can get driving force. Then we can get a driving force existing, the driving force being the concentration difference. And as a result of the driving force difference, you will get mass transfer taking place. Variables affecting equilibrium of a solute are temperature, pressure, and concentration. When we talk about a solute, what are we talking about? Again, we're talking about that particular component that will be able to move from the one phase to the other. Okay, so we term that the solute. The variables that affect this equilibrium that we're talking about are temperature, pressure, and concentration. Okay, so temperature is basically a temperature of the entire system. Pressure is a pressure of the entire system. We don't talk about the difference in pressure between the liquid phase and the gaseous phase, or the difference in pressure in temperature between the liquid phase and the gaseous phase. They're both under the same conditions. Okay. However, concentration will be different. So if we've got two phases existing, you've got the liquid phase and the gaseous phase. Okay, or two liquid phases. Okay, when we talk about liquid-liquid extraction, you've got two liquid phases. So whatever the difference, we've got two phases that are existing, and there's concentration difference. And remember, we must have concentration difference. That is how we get mass transfer. Okay, so when there's concentration difference, we will be able to move the solute from one phase to the other. So therefore, concentration is not just concentration of the system. We talk about concentration of concentration in a particular phase. So if you've got a gaseous phase and a liquid phase, you talk about the concentration in the liquid phase and the concentration in the gaseous phase, because they could be different. How do we determine number of degrees of freedom? So the equilibrium between two phases is given in a given situation is restricted by what we call the phase rule. That is the rule that we apply. It says F is equal to C minus P plus 2. F, degrees of freedom, how many variants do we have? Okay, how many things that you can change arbitrarily. You can specify these values. Okay, they're not determined by the system. You can specify it. That's the degrees of freedom. C is the number of components in the systems, and P is the number of phases at equilibrium. Okay, so we did an example where you have CO2, air, and water. So CO2, air, and water, your air is your inert air. So in other words, inert meaning that it will only stay in the gaseous phase. It's not going to condense. Remember, we spoke last week about the difference between vapor and gas. Okay, so here the air is non-condensable. Okay, so it's not going to move. It's not going to dissolve into the water. It's going to stay in the gaseous phase. The water itself is in the liquid phase. Once again, the liquid phase, it's going to stay like that. It's not going to move into the gaseous phase. Okay. The CO2 is the solute, so it exists in the gaseous phase, but we may use water in order to absorb some of that CO2 into the water. And what do we do by that? Or what is the result of that? We are then changing the concentration of the CO2 in the gaseous phase. If we're changing the concentration of CO2 in the gaseous phase, we're removing some of the CO2, we're reducing its concentration. And the concentration in the water phase, in the liquid phase, will start to increase. Okay. So if we've got this system, CO2, A, water, how many components? CO2, A, water. Okay, so 3 components. How many phases? You've got the gaseous phase and you've got the liquid phase. Okay, so 2 phases, which means that you've got 3 degrees of freedom. F is equal to 3 according to the phase rule. F equal to 3, what does that mean? It means from all those variables that we spoke about, temperature, pressure, concentration in the liquid phase, concentration in the gaseous phase, from all of those, 3 of those variables I can specify arbitrarily. Okay, I can't specify 4 because I don't have 4 degrees of freedom. I only got 3 degrees of freedom. All right. So what it's saying there is that if temperature and pressure are set, so if I'm working under certain conditions where we've got pressure that is predetermined, it's already set, the temperature is predetermined, then it reduces the degrees of freedom to just 1. Okay, and 1 variable may be set arbitrarily. So if, for example, we specify the concentration in the liquid phase, we use the symbol X for mole fraction or mass fraction in the liquid phase. We use the concentration, the symbol Y for mole fraction or mass fraction in the gaseous phase. Then Y, if XA is specified, it is set. So in other words, I'm telling the system, I want a certain concentration X in the liquid phase. Then I can't specify what is in the gaseous phase. You understand? The system itself will automatically determine that value, because at equilibrium, only 1 value will match this concentration that we have in the liquid phase. Only 1 value of YA will match that concentration. So the equilibrium will determine that particular value. Okay, so that's what degrees of freedom is all about. I think that is where we stopped last week. So let's move on. Gas-liquid equilibrium data. So if we're talking about equilibrium, it means that this data must be readily available. In other words, at a particular temperature and pressure, I should know, if I've got 2 systems, what the relationship will be between the concentration in the gas phase and the concentration in the liquid phase. It should be readily available, and it is. So if we go to equilibrium data, and you'll find them in many of the textbooks, it will tell you for a particular system. In this particular case, they're talking about SO2, okay, in the diagram. If you've got SO2, SO2 will exist in equilibrium between the gaseous phase and the liquid phase according to this graph. Okay, so this data is readily available. So let's consider the system, the SO2 system. So you've got 3 components. You've got SO2, which is the solute. You've got A, the inert gaseous phase. You've got water, which is the inert liquid phase. They are put into a closed container. You mix them under constant temperature and pressure until equilibrium is attained. So you're bringing these 2 systems, these 2 phases into equilibrium. Okay, you're mixing them, they're in immediate contact, and you allow equilibrium to take place or to be established, and then you measure the concentrations in the liquid phase and the gaseous phase. Okay, so it says samples of the gas and the liquid are removed and they're analyzed in order to determine their concentrations in the liquid phase and the gaseous phase. So once again, the symbols that we use for concentrations. How do we determine concentrations? We talk about in the liquid phase, we'll use the symbol X. X can be for mole fraction or mass fraction. Okay. Now, in distillation, in absorption, we always use a mole basis. Why do we use a mole basis? Because moles affect the pressure directly affects the pressure in the gaseous phase. Okay, so therefore we always use a mole basis when we talk about distillation and absorption. Later on, when we're talking about liquid-liquid extraction, you'll see we'll change the basis. We'll then start talking about mass basis. So for the first two sections, absorption, distillation, we'll always use mole basis. For liquid extraction, we will use mass basis. So we use the symbol X. Okay, so therefore you can see on the x-axis, you've got mole fraction of SO2 in the liquid phase, that is XA. On the y-axis, we can have Y. Now Y is the concentration, the mole fraction of SO2 in the gaseous phase. Mole fraction of SO2 in the gaseous phase. We can use Y, but because we're talking about a gas, we can also use pressure, because we know there's laws that exist that say that pressure is directly related to the mole fraction of the component in the gaseous phase. Okay, what is that law called? Anyone? Do you remember your chemistry that you did in your first year?
I think it's ideal gas law.
Say again?
Ideal gas law.
Ideal gas law. Ideal gas law says you can manipulate the ideal gas law, right? So you can use different symbols for the ideal gas law. But what it does is that it relates pressure to concentration. Okay. There's other laws that says, like for example, Dalton's law, that it says that the sum of the partial pressures is equal to total pressure. Okay, so you can see that there's a direct relationship between concentration, which is mole fraction, and pressure or partial pressure. Therefore, in a gaseous phase, it is easier, instead of using concentration or mole fraction, it is easier to use partial pressures. And as you can see here in the y-axis, our concentration is reflected as partial pressures. Partial pressure of SO2, which is our solute. In the gas phase, we use the symbol small p subscript A. A is the solute, which is SO2 in this case, and the P is the partial pressure. So that relationship, as you can see, the solid line is the actual relationship. Okay, the solid line is the actual relationship. The dotted line or the dashed line is an approximate. So the solid line, you can see, is not a straight line. Okay, it's not a straight line. But we can try and approximate it using a straight line. And that is why we use this, this dashed line. Okay, so the dashed line is now called or is associated with the Henry's law. So it says that there is a direct relationship, direct proportional relationship between partial pressure and X, PA and XA. Okay, so what is that relationship? PA is equal to some constant times XA. So there's a direct proportional relationship. The constant of proportionality is Henry's constant. Okay, and in this case, for SO2A system, the Henry's constant, you can find this in tables. It is 29.6. So what does this do? This tells me that at any value, PA is equal to 29.6 XA. At any value of XA, I can find the equilibrium concentration or partial pressure in the gaseous phase. Similarly, if I know PA, I can find the equilibrium value XA. Okay, so let's go back to degrees of freedom. When we spoke about degrees of freedom, we said that you've got 4 variables that we talk about: pressure, temperature, concentration in the gaseous phase, concentration in the liquid phase. If I know that I'm mixing these two systems at constant temperature and pressure, then those 2 variables are already specified, temperature and pressure. As a result, I can only specify one of those concentrations. I can either specify PA, use Henry's law to calculate XA, or specify XA and use Henry's law to calculate PA. Okay, I hope you're with me, people. So let's go more into detail with regards to Henry's law. Often the equilibrium relation PA in the gaseous phase XA can be expressed by a straight line. PA is equal to HXA, and the H is Henry's constant. Okay, Henry's constant. Unfortunately, we still use Henry's constant from data tables that are not in SI units. So therefore, you can see Henry's constant is its units is atmospheres per mole fraction. Atmospheres per mole fraction. In other words, if I multiply that, which is H by XA, which is mole fraction, then I'm going to get partial pressure in atmospheres. Okay, so it's not in kPa, which means that when I'm specifying values to use in this law, I must always use partial pressure in atmospheres. So even if it is given to you in some other variable, in some other units, I've got to convert it to atmospheres in order to use in this equation. So we spoke about partial pressure and XA, okay? But we said that partial pressure was related to mole fraction. And what is that relationship? Partial pressure over total pressure. Okay, PA is the partial pressure for the particular component. Capital P is the total pressure of that system. That is equal to mole fraction. Okay, as a result, I can take this equation and convert it into a relationship between YA and XA. How do I do that? I simply divide the entire equation by P. Okay, so now I've got a relationship YA versus XA. This is also still called Henry's constant. Okay, H, but we use H prime in order to differentiate it between the top one and the bottom. So we use H prime here. H prime units now becomes mole fraction per mole fraction of the gas per mole fraction of the liquid. Okay. But it is dependent on total pressure, as you can see. So the H values I'll be able to read off tables. I can get that from tables. The H prime, I can't get that from tables. In order to use H prime, I've got to take the H values that I've got from tables and divide it by the total pressure of my system. Okay, in order to get H prime. Hopefully you've understood.